Okay, so this is just a quick video that kind of goes over all the formulas that you need to know. Most of these things make intuitive sense. We're talking about parametric equations where instead of um, defining y as a function of x, you're defining both x and y as a function of some external variable, which is almost always time. So t for time. And you have to, if you haven't had physics, you have to review vectors a little bit, but I find that 99% of your students have some familiarity with vectors. So I'm just going to assume that you understand a little bit about them. The position vector S of t is given by x as a function of t, y as a function of t. If you're asked, and these will be, if you get this, these will be some of the easier APFRQ problems, I think. You might be asked for the velocity vector. Velocity vector is just given by the derivatives of each of these, still listed in component form. So x prime of t, comma y prime of t. And the acceleration vector, a of t, is going to be the same thing written as components, second derivatives for each of those, like you'd expect. Now, speed is a little bit different. Speed is velocity is the absolute value or the magnitude of velocity, which is going to be the square root of dx dt squared plus dy dt squared. And if you think of what that is, like if I have some function, let's say this is x and this is y, and it's defined as a function of t. If I want to know what the velocity is, I could think of it as a triangle, right? And this would be a crude, but still an approximation. This you could think of as dx dt. This you could think of as dy dt. And this is the velocity, which is equal to the square root of dx dt squared plus dy dt squared. Okay, all that I think is pretty straightforward, and I don't expect you to have much of a problem with it. The things that we come into next can be a little bit confusing. Slope. Okay, so the slope of a function is dy dx, and that you get from doing a ratio of dy dt divided by dx dt. That's simple enough. But concavity is not what you would think. What you would think would be d squared y over dt squared over d squared x over dt squared. But that's not it, and that's one of the trickier parts of this whole thing. Concavity is when you take the derivative with respect to x of dy dx, which is, let's say you have dy dx, your slope function. I'm going to take that derivative with respect to t, and I have to divide that by dx dt. And that equals the concavity, or the second derivative function, d squared y over dx squared. And you don't need to know why that is. These things you just kind of have to accept that it is for the purposes of the AP test. But we can look at an example where I have, let's say, x is equal to cosine of t and y is equal to 2t. And you might want to put into Desmos exactly like the notation that we're used to. X sub t is equal to, what did I say, cosine of t? But actually, that doesn't work. This isn't. Desmos doesn't recognize this as parameter or vector form. What you have to do in Desmos is you have to write it as an ordered pair with both pairs having some kind of t in there. So what I said was x is equal to cosine t, y is equal to 2t. So I'm going to write them as an ordered pair, and you can play with this t parameter to get a longer curve if you're into that kind of thing. But so that's what it looks like. That's cool. Let's say I want to know what the slope function is in what the concavity function is. So let's say dx dt is going to equal negative sine of t. dy dt is going to equal 2. dy dx is going to equal 2 over negative sine of t, which I believe should be 2 cosecant, negative 2 cosecant of t. And now, what's the concavity function? Well, this is going to be the derivative with respect to t of negative 2 cosecant of t divided by the derivative with respect to t of negative sine of t. And when I first looked at this, I thought, oh, that's going to be some kind of quotient rule. And I was like, hell no. But then I realized, oh, it's not actually the quotient rule. So I think I can do this. What if I do this, I'm going to get, I think the derivative of cosecant is negative cosecant cotangent. I haven't looked that up to make sure that I'm right. So there's always the possibility that I'm wrong. But if I'm right about that derivative, then that should be the derivative of that. Negative sine should be negative cosine. So this turns into 2 times 1 over sine of t times cosine of t over sine of t times negative cosine of t over 1, which would be negative 2 cotangent squared of t. There's definitely a chance I made some kind of mistake in there, but going back and checking my answers, that's kind of below my pay grade. So you'll have to let me know if I did. But that's what I believe. That's definitely the right process for finding the concavity of a parametrically of a component form vector. And of course, if you want to know at a certain point, you'd plug in the t and find out if it's concave up or concave down based on whether it's positive or negative. As far as arc length goes, if I go back to this picture of the velocity, let's say, oop, that's my velocity, but this is calculus, so we're going to think about it in terms of a lot of little smaller steps. So I might think of there to there, there to there, there to there, there to there, there to there. And I can think of this as a dx dt, dy dt, dx dt, dy dt. Right, where this is dy dt and this is dx dt. And the formula for arc length, which is much easier than the one you used to have, which is can't remember what letter, we use the letter S to represent it, is the integral dx dt squared plus dy dt squared. And it's the integral from a to b. And when it was in, I think it's worth mentioning that it used to be square root of 1 minus dy dx squared. And you should know that there's two different formulas for arc length, and you should know that it's easier when it's, I think the parametric is usually easier because you don't have to manipulate the function much. But where people will go wrong and it'll cost them a lot of time and it will not gain them any extra points on the test is they'll start trying to convert between the two forms. If you're given it in parametric, use the arc length for parametric. If you're given it in y as a function of x form, then just use this one here. All right, good luck, everybody.